All right, so now let's talk about like what is the central concept of this chapter, which is this concept of aromaticity. So what the heck does that mean? Well, so first of all, we got to rewind. Like I said, benzene was really old, is a really sort of like early bird discovery in the history of organic chemistry. 1866 is when this particular guy, Auguste Couclet, proposed that it was a structure that consisted of alternating double bonds, right? This sort of idea of resonance. First of all, 1866, that's like 250 years ago. That's crazy. Crazy long time ago. And one of the things that, so one of the things that was sort of special about this molecule and puzzled people at first was that they knew it consisted of these 3 double bonds and these 3 single bonds. But the problem is that all those bonds were the same length, right? Because we know that double bonds are shorter than single bonds. So what you would expect is a structure, let's see if I can draw it, that looks something like this, where those single bonds are longer. You wouldn't expect it to be a symmetric structure that it is. So that's why the first proposition of resonance came about. And so now we sort of know that there is this resonance that resonance structures, you can represent it with the circle in the middle or by drawing both resonance structures. Remember that this is kind of the more correct way. I know that this way is easy and everybody wants to go for that, but when we're drawing resonance contributors, the problem is that this doesn't show you how many electrons are actually in there, right? Whereas drawing all the resonance contributors does. Nonetheless, you will see the circle convention. The other thing about benzene that was really puzzling was that it was not reactive in the same way that alkenes are, right? I mean, if it's just got 3 double bonds, you would expect them to behave like normal alkenes, just with 3 of them. Remember, alkenes will react with liquid bromine to form the di-substituted compound here, right? We have those addition reactions. No such reaction is observed with benzene, okay? And this idea is that benzene is aromatic, and I'm going to explain exactly what that means in a second, but just bear with me. We're going to use that word. Aromatic compounds are remarkably stable, okay? What you would expect based on sort of the trends of when I have 1 double bond and I reduce it, it releases a certain amount of energy. Well, if I have 2 double bonds, that releases about twice as much energy. If I have 3 double bonds, you would expect it to release 3 times the amount of energy, when in fact it does not. It releases a really small amount of energy, okay? Again, this is just a reflection of, on this free energy diagram where benzene is, it is quite stable, quite low in energy, okay? And we're going to see that this is similar to what we were talking about with conjugated dienes. Remember, when dienes are conjugated, they are remarkably stable compared to when they're isolated. This is a very similar phenomenon, but aromaticity takes up conjugation to like the next level. It's like really special type of conjugation. Not all fully conjugated rings are aromatic, though. Not all of them have that aromatic stability. So 2 famous examples is cyclobutadiene and cyclooctatrine. These are not remarkably stable at all, and they undergo reactions just like alkenes do. Okay, so if you put liquid bromine in there, you would expect to see that sort of addition reaction. So we're going to go through and we're going to basically, we have rules for what would make a compound aromatic, and we're going to be able to then go in and classify compounds as either being aromatic or falling into another category here. So let's focus on this aromatic definition real quick. And again, remember that benzene is this like quintessential aromatic compound, okay? So to be aromatic, you got to meet 2 rules, okay? So you have to be a fully conjugated ring with overlapping p orbitals. What does that mean? It means that every atom in that ring has to have a p orbital or be, another way of saying that is sp2 hybridized, right? Remember when your sp2 hybridized, your s orbital mixes with two p orbitals to form your sigma bonding, but you have that one leftover p orbital that sticks up. So in this case, this compound, this benzene, has these p orbitals that are sticking up above the ring, right? Similar, exact same concept that we needed to be a conjugated diene, right? You had to have that sp2 hybridized carbons all in a row. If there was anything sp3 hybridized in the middle, it would mess it up and make it an isolated diene. Same idea here, right? Fully conjugated ring with overlapping p orbitals. Again, another way of saying that is that everybody in that ring has to be sp2 hybridized, okay? The other criteria, and this is weird, this is not one that's really intuitive, is what's called Hupple's Rule. And it states that the number of electrons in there, the number of electron pairs, has to follow a certain sequence, which we call the 4n+2. Now, one of the confusing things about this is that people see this 4n+2 and they immediately think that we have a math problem on our hands. That's not what 4n+2 is. This represents what would be, in nerdy math terms, called a series. It really represents, it's a shorthand for a series of numbers. So if you plug in n equals 0, that gives you 2. If you plug in n equals 1, that gives you 6. If you plug in n equals 2, that gives you 10. If you plug in n equals 3, that gives you 14, et cetera, and this could go on to infinity, right? But 4n+2, what it is a shorthand for these series of digits here. 2, 6, 10, 14. I guess the next one would be 18, 22, et cetera, in infinity. So this isn't a math problem. You're not solving for n or anything like that. 4n+2 is a rule, and it's a shorthand for this series of numbers. So basically, in order to be aromatic, you have to have either 2 electrons in the ring, 6 electrons in the ring, 10 electrons in the ring, et cetera, So let's just double check that that is the case. For this particular compound here, we have 2 electrons in this pi bond, 4 in this pi bond, and 6 in this, or rather total 6. So that meets our aromatic criteria. Another way of saying this same sort of idea is that the number of pairs of electrons has to be odd. So in this case, we have 3 pairs of electrons. That's an odd number. Right? So anyway, that's the next second rule, is the number of electrons has to meet this particular criteria, this Hupple rule. So remember we said that cyclobutadiene was not, right? Let's convince ourselves of why that is. Well, it does meet rule 1. It has fully conjugated ring system, meaning that all these guys are sp2 hybridized. They all have a p orbital that can engage in conjugation. The problem is that there has 4 electrons in that conjugated ring, which does not meet Hupple's rule. When that's the case, right, when we meet criteria 1 but don't meet criteria 2, that compound is called anti-aromatic, okay? We're going to see that aromatic compounds are remarkably stable. The opposite is true for anti-aromatic compounds. They're remarkably unstable, even more than you would expect. Okay, so anti-aromatic means that you still have a fully conjugated ring with overlapping p orbitals, but you have an even number of electron pairs. Another way to say that is that it does not meet that Hupple's rule. Okay, if you don't meet criteria 1, then you're just called non-aromatic. Okay, so an example of that would be, you know, if I took away this bond here, now I have, whoops, sp2, 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 but now I have these sp3 molecules. So I don't have a fully conjugated ring with overlapping p orbitals. So this compound would be considered non-aromatic. Okay, so that's going to be the name of the game for this particular chapter, is classifying, lecture, is classifying compounds as aromatic, anti-aromatic, or non-aromatic based on these rules. Okay, again, we had said that cyclobutadiene doesn't meet that rule, so it's anti-aromatic. Let's look at this famous example as well, cyclooctatrine. It has that fully conjugated ring, right? So it meets criteria 1. Everything has a p orbital that can participate in conjugation. However, we have 2, 4, 6, 8 electrons, or 4 pairs. So we do not meet Hupple's rule. So this is again an example of an anti-aromatic compound. So let's just do a bunch of examples real quick so we can get a sense. If it's a great idea to pause and try to do as many of these as you can. Remember, the goal here is to classify these as being aromatic, anti-aromatic, or non-aromatic. So yeah, give it a try on your own and be good practice, and then you can play and watch me go through it and make sure that you got it all correct, okay? So first of all, benzene, we sort of already know this one to be true. Nonetheless, I'm gonna use this blue shorthand here for sp2 hybridized carbons. So I indeed have all sp2 hybridized carbons, giving me that conjugated ring. And then I have 2, 4, 6 electrons. So that meets that Hupple's rule, that 4n plus 2 rule. Remember, by 4n plus 2, I'm really talking about a series of numbers: 2, 6, 10, 14, 18, ... Okay, so what about our next example here? Let's see if we can't classify that. So rule 1, do I have a fully conjugated ring with overlapping p orbitals? Well, this is sp2. I can't spot any sp3 hybridized carbons, so that's good. So I meet rule 1, check. What about rule 2? I have 2, 4, 6, 8, 10. So does this meet Hupple's rule? It does. This is also aromatic, just like this one. All right, what about the next compound here? Here I have sp2 carbons here, but notice that this guy here is going to be sp3 hybridized. So that means that I do not meet rule 1. What do we call it when we don't meet rule 1? This would be non-aromatic. Same thing over here in this example. Although all these guys are sp2 hybridized, I have this one in the ring that's sp3 hybridized, messing it up. So this is non-aromatic. I mean, just to note, these bonds are still conjugated. Like, going back to what we learned last time, this is certainly an example of a conjugated diene. This example here, we actually saw this compound participating in these Diels-Alder reactions. Nonetheless, although they're conjugated, it's not aromatic. Aromatic is now this special type of conjugation that's specific to rings. We did cyclobutadiene. Remember that that one met rule 1, but failed Hupple's rule, which made it anti-aromatic. Okay. Now notice these ones. Now we have some ions in here. That's a little interesting. So let's just go through again. Does it meet rule 1? Well, we know that these carbons are certainly sp2 hybridized. What about this one? Remember, carbocations are indeed sp2 hybridized, and that p orbital is empty. Okay, so this is an example of a fully conjugated ring that has just 2 electrons in it, which is one of the numbers in our Hupple's rule series. So this is an example of an aromatic compound. What about this one over here? Well, These guys are sort of obviously sp2 hybridized. If you don't remember hybridization, it's a good idea to look at chapter 1, and in particular, there's a YouTube video posted from chapter 1 about hybridization. It's kind of going to be an important thing to remind yourself of. It's pretty simple too, so go back and review it. It won't take long to refresh your memory. And then we have that, again, that carbocation, which we know is sp2 hybridized. That lone pair, or the p orbital, is what houses that positive charge. It doesn't have any electrons in it. However, this compound has 4 electrons in it, right? Because this is a positive charge. That means there's no electrons contributing from that atom. So this one is an example of an anti-aromatic compound. Right, it does not meet, it meets rule 1, but does not meet rule 2. It does not follow Hupple's rule. Okay, yeah, cool.